Okay. And in fact, if you don't mind, I'll start the video from yours.
Perfect.
I'll do a little bit of video also. We should also unmute.
No, that one's picking up the sound.
Yeah, because otherwise, Milan is not going to hear me.
Sorry, I defer to the expert. Okay, super. So delighted to have Raoul back. Thank you, Cesare, for producing such a great student. Raoul received his BSc honors and MSc from UCT for earning a doctorate in theoretical physics at the University of Oxford in 2012. Subsequently, Raoul had postdoctoral positions at Fermilab in the US, Karlsruhe Institute of Technology in Germany, before becoming a fellow in the theoretical physics department at CERN in 2018. In 2021, he was appointed associate professor at the University of Milan. The focus of his research is the development of methods to perform calculations of pure quantum chromodynamics and the application of those methods to make high-precision predictions of phenomenology at the Large Hadron Collider, with particular emphasis on the physics of the Higgs boson. Very exciting. We're delighted to have you. Thank you for coming.
Thanks for having me. It's wonderful, a bit surreal, but wonderful to be back here. I know that I am sort of what stands between you and a long weekend, so I'm going to try and be as entertaining as possible. So I'm going to discuss some of my work on the precision physics program at the Large Hadron Collider. And as advertised, I'm going to try and make this as accessible to non-experts as possible, meaning that if you're an honors or a master's student, hopefully you'll be able to follow most of what I'm saying, or at least some of what I'm saying. I'll get into some of the details of my research towards the end. If you're interested in some of the technical details, I'm very happy to. I'll be around for the rest of the afternoon. I'm very happy to discuss things with you. So let me just start off by saying what I understand as the place of particle physics within the broad. Yeah, you can really that. Okay, within the broad field of physics. So we have this idea of reductionism, where we can understand the world around us by probing smaller, more fundamental structures that underlie the complex phenomena. So we go from chemical elements or reactions to molecules, which are made of atoms. Atoms consist of a nucleus surrounded by a bunch of electrons. Inside the nucleus is made of protons and neutrons, and the protons and neutrons themselves are made of quarks, which together with some other particles constitute the most elementary fundamental particles for which we have experimental evidence. And although there are some drawbacks to reductionism, and it's very interesting to study the emergence of complex phenomena from simpler systems, there's no denying that it has made enormous progress in helping us to understand the natural world. And the forefront of the reductionist approach is particle physics. So if we want to probe these smaller, deeper, more fundamental structures, we need a microscope or at least an experiment to do so. And there are a number of experiments running within particle physics, but the one that I'm most interested in, or the ones I should say, that I am most interested in are those at the Large Hadron Collider at CERN in Geneva, where proton beams are accelerated to very high energies. Actually, this number is slightly wrong because I think they're at 13.6 now. But nevertheless, very, very high energies. The beams are going in very close to the speed of light, and then they collide. In the collisions, you produce no, it's okay. Okay. We produce a large amount of energy, and that energy allows us to create all sorts of particles, which then go are detected, observed, and their properties can be understood, and we can try and explore these fundamental interactions in a controlled environment. Is the most important thing. Now, I'm not an experimentalist, so that's really the limit of what I understand about the actual machine. I'm a theorist, so I'm much more interested in understanding how we can make predictions for what is happening at the Large Hadron Collider that we can then confront with the experimental data and try and learn something. So for sure, we're at very high energies, meaning the form momentum squared of the particle is much larger than its rest mass squared, which means we better use special relativity. And we're talking about very, very small particles at the subatomic level, so we better be using quantum mechanics. And these two can be brought together in a mathematical framework called quantum field theory, called QFT. And this is very much the language of elementary, or if you like, high energy particle physics. When you combine quantum field theories with the notion of gauge invariance, and gauge invariance is kind of an extension of the gauge invariance that you know from classical electromagnetism. In the context of quantum field theory, gauge invariance is understood as some local rotation in some abstract space. You can think of it as kind of like a phase rotation, but where the phase differs at every point in space and time. That's called, that is mathematically called an abelian U1 gauge symmetry. And if you impose this U1 gauge symmetry, then you get a theory called quantum electrodynamics, or QED, which is the quantum field theory that fully explains the electromagnetic interactions. In particular, it understands electromagnetic interactions through the exchange of force-mediating bosons, which are the photons that we know that we see whenever we turn on the light, or if the weather's nice, we see from the sun. So when I see something like an electron coming in, scattering off a positron, and then an electron and a positron going out, I can understand these as the electron line exchange and the positron line exchanging a photon. Or equivalently, I can think of the electron and the positron annihilating each other, producing a photon, which then creates an electron and positron pair. In either way, this force is mediated by this massless photon. And this is a very nice theory. You can compute something in this theory called the anomalous magnetic moment of the electron, and you can compute it to a very, very high precision if you're sufficiently crazy enough to do so. And then you can go and make a measurement of it, and you see that they agree to very high precision, something like 10 significant figures, which I believe is one of the best measured quantities, the quantity in all of science where theory and experiment best agree. You can do a similar thing in order to explain the strong nuclear force. In this case, your symmetry has to be slightly more complicated. So you have, instead of an abelian U1 symmetry, you need to ask for a non-abelian SU3 symmetry. But then you get a very analogous theory. Now you have the strong force carried by particles called gluons, which similarly are massless. So they're the analog of photons in the theory of QCD. Photons couple to electromagnetic charge, so objects that are either positively or negatively charged. And in a similar way, there is a charge for gluons that they couple to, which is called a color charge. Now, the standard thing is to say this is not the color that we see in everyday life. It's just the label, in much the same way that positive and negative are just labels. It's not that an electron is negative because it has a slightly pessimistic view on life. It's just a name. And by the way, you can see how long I've been outside of South Africa, spelling color in the American way.
I strongly approve.
You strongly approve. Yeah, I'm. This dropping the U and the last letter of the alphabet. Within one sentence, I can go between Z and Z boson. It's an absolute nightmare. Because in America, when I got to America, I would say, "Oh, it's a Z boson," and they'd say, "Oh, we've discovered a new particle." So I learned very quickly I had to call it a Z boson. And then when I moved back to Europe, it's stuck. I don't know. Anyway, I think a lot of these slides were taken from. Maybe I gave a talk in the US. Anyway, so the gluons, so the photons themselves do not have an electromagnetic charge, so they don't interact with each other. Gluons, on the other hand, do have a color charge, so you have self-interactions. So you may have a diagram where a line of quarks radiates some gluons, but you might also have this 3-point interaction between this gluon and these two gluons. This is a short-range force. We don't see it at the classical level, unlike electromagnetism, which of course we see classically. So this idea of gauge invariance is a very important principle, as I've explained, or at least said. It allows us to have quantum field theories of 2 of the 4 fundamental forces, the strong and the electromagnetic force. There are 4 fundamental forces. Quantizing gravity is difficult. It's probably the single biggest outstanding challenge in theoretical physics. People might disagree, but in my opinion, that's certainly the case. And it's as my opinion is that we're not anywhere close to finding a quantum theory of gravity. So let's put that to one side. This idea of gauge invariance is also very closely linked to conservation laws, such as the conservation of electric of charge in QED. This is through a very beautiful theorem called Noether's theorem. And it also limits the more pathological behavior of quantum field theories, things like anomalies, renormalization, and so forth. More, let's say, more technical topics. Okay, so that's the strong force, the electromagnetic force. Okay, gravity is very difficult. What about the fourth force, the weak force? This is something that we know from, for example, beta decay, and we can understand it through a Fermi theory where we have a sort of a 4-point interaction between, say, a muon decaying to an electron and two neutrinos, a neutrino anti-neutrino pair. It turns out this is just a low energy approximation to a more complete quantum field theory, where again we have this force mediated by a vector boson. The problem is that in order to match experimental evidence, this vector boson needs to have a mass, whereas the gluon and the photon have to be massless. And the reason that this is a short range force is because this boson is massive. Now, the problem with this is that if you just take a Lagrangian and you put in a mass for a gauge boson by hand, you're going to break gauge invariance. And I've just told you that gauge invariance has all these wonderful properties that come with it. So we really, really would like to keep the principle of gauge invariance alive, but we need to give a mass to these bosons at the same time, because that's what the experiments are telling us needs to happen. So what we want is a dynamic origin for the gauge boson's mass. And this can be obtained through a mechanism called spontaneous symmetry breaking, which was a concept that first arose in theoretical statistical physics or condensed matter physics and was imported into particle physics from that from that community. So the idea, and this is the very celebrated Higgs mechanism. So the idea is you start off with a large electroweak symmetry. Formally, it's called an SU2 cross U1 symmetry, but that doesn't really matter. You can think of this as just some big symmetry. And then you imagine that you have a field with some potential given by this formula. Because of the structure, the form of this potential, this Higgs field has a non-zero ground state. Formally, in quantum field theory, this is called a vacuum expectation value. You can just think about this as the ground state. And this leads to something called electroweak symmetry breaking. So you have this famous so-called Mexican hat potential, which you can see is completely rotationally symmetric. And the point of maximum symmetry is if an object, a ball, sits right at the top of the hat. But of course, that isn't the point of lowest energy. This ball is going to want to roll down and sit somewhere inside the trough. As soon as it does that, it's broken the symmetry. So if it sits here or here or here or anywhere within the trough, the particular position of that ball has broken the symmetry. The ground state has broken the symmetry. But of course, the whole system, that potential, retains the symmetry. And that's exactly what you have in electroweak symmetry breaking. The gauge invariance is maintained at the level of the Lagrangian, but it's broken at the level of the ground state, the vacuum expectation value. And this is the so-called electroweak symmetry breaking. It turns out through, you do some mathematics, and you see that this gives mass to the electroweak gauge bosons, the so-called W and Z bosons, as well as the charged fermions. So those are things like electrons, muons, taus, as well as the quarks, but it keeps the photon massless, which is important because we observe we have to very high accuracy experimental evidence that the photon is indeed massless. And then we still have some quantum excitations of this Higgs field, and that leads us to we call this the Higgs boson, the famous Higgs boson. So if we combine all these things, the theory of the strong force QCD, the electroweak theory with spontaneous symmetry breaking through the Higgs mechanism, we get the standard model of particle physics. It's both mathematically consistent as a result of the Higgs mechanism of electroweak symmetry breaking, and incredibly concise. And concise enough that you can go to the gift shop at CERN, and for only 20 Swiss francs you can buy yourself a mouse with the standard model Lagrangian on. In Switzerland, 20 francs is about the cost of a cup of coffee. That's not that expensive. Okay, so this is the particle content of the standard model. On the outer ring, I guess, we have the spin half fermions. So at the top, in the sort of, I don't know, reddish orange color, are the quarks. These are the objects, the particles that experience the strong force, so they have a color charge, the weak force, so they have a so-called flavor. It's not University of Cape Town, it's up charm and top, down strange and bottom, as well as an electromagnetic charge. They couple to the electromagnetic force. At the bottom on the left, we have the charged leptons, which experience the weak and electromagnetic force. And on the right, we have the neutrinos, which only experience the weak force and therefore interact very seldom. And for almost all of the LHC experiments, don't really play any role whatsoever. There are a few exceptions, but for the most of the time, we just see them as something that is missing. In blue, inside we have the spin 1 gauge bosons. This is the photon for the electromagnetic force, the gluon for the strong force, and then at the bottom, the massive W and Z bosons for the weak force. And then right at the center, the scalar spin 0 Higgs particle. And I put this, I like this plot in particular because it has the Higgs at the center, which is really, I think, exactly where it belongs. I just want to give you some idea of the scales involved, because this is going to be important for what I say next. So we know that the proton has a mass pretty close to 1 GeV. The electron has a mass many times about 3 orders of magnitude smaller than that. Most of these, the W and Z bosons, have a mass much larger, around about 80 and 91 GeV respectively. The Higgs mass is about 125 GeV, and the heaviest particle is the top, sitting over there, which has a mass of 173 GeV. I think this is about the same mass as that of the nucleus of gold, despite being a fundamental particle, which is pretty interesting. So typically, when we talk about processes that are happening at what I call the electroweak scale for these bosons, we're talking about energy ranges in the region of 100 GeV and above. And of course, this was theorized in the 50s, 60s, and 70s, and we had to wait till 2012 while I was writing up my PhD for the discovery of the Higgs boson, which put all of this on a firm experimental footing, as well as being so mathematically appealing. But of course, like any good science, once you discover something, that's not the end of the story. A discovery should raise further questions. And I think the biggest one that the Higgs boson raises, in my opinion at least, is, do we really see the electroweak symmetry breaking exactly as we have in the standard model? Now, the Higgs potential in the standard model is really remarkably simple. It just looks like this. This is basically just the first introductory example you get in a quantum field theory course. And so it's weird for something this simple to be at the heart of all our understanding of fundamental interactions. So we can ask, is this really what is realized in nature? We know that the Higgs electroweak symmetry breaking is responsible for the masses of these elementary particles, but we can ask, is it the only thing that's responsible for these masses, or is there some other effect that we've yet to detect? Fundamental scalar fields are weird. And the Higgs is the only one that we see. So we can say, is this Higgs really a scalar field? And so all of these and more questions motivate in-depth investigations of the Higgs boson in order to understand this mechanism of electroweak symmetry breaking. And just to give you an idea of how important this might be. So I've told you that the Higgs mechanism gives fermions masses, and it happens to do so in a way that down quarks are heavier than up quarks, as we showed in my master's thesis. And this means that neutrons, which are made of 2 down quarks and an up quark, are heavier than protons, which are made of 2 up quarks and 1 down quark. As a result, neutrons can decay into protons, and protons do not decay into neutrons. If it were the other way around, protons would decay into neutrons, and you wouldn't be able to get a stable hydrogen nucleus, which means you wouldn't be able to get stable atoms or stars or humans or anything complicated. So ultimately, the fact that we're here is due to the Higgs mechanism in some way. Okay, and there's a lot of stuff to explore about the Higgs boson, its fundamental properties such as mass and spin, how it couples to other particles, how it couples to itself, which is related to this potential, its high energy behavior, etc., etc. And it turns out that the LHC is very good at measuring stuff related to the Higgs boson And as you can see from this plot, maybe, I don't know if you can see the x-axis, these are the measurements of the coupling of the Higgs to the various other particles. And this is 2% and this is 4%. This is over the lifetime of the Large Hadron Collider, which should be the next 15 or 20 years. And so you see that for most of the time, we're between the, say, 2 to 4% level. And of course, this is a projection, and typically these projections are wildly pessimistic because people are smart and people work hard at this sort of stuff. So they end up improving. In fact, I think for at least some of the measurements, the current results that they have are better than what was predicted 10 years ago over the entire lifetime. So they've already exceeded what they should, they've already done better than where they should be in 2040. And so this tells us that if this is what the experimentalists are going to do, then us as theorists, we need to match them with theory predictions in the percent level. Now, I've been spending I've spent the last 15, 20 minutes singing the praises of the standard model, but of course, we know that this cannot be the complete picture of nature. As I said, gravity is not included in the standard model. We have lots of evidence for dark matter. There's no dark matter candidate in the standard model. The standard model doesn't explain neutrino masses or antimatter asymmetry, and so forth. And so we typically would like to think that there is some physics beyond the standard model. And we've looked, and when I say we, I mean people at the LHC have looked very hard, but they haven't found any direct, concrete, incontrovertible evidence of beyond the standard model physics yet. What they have been able to do is put constraints on masses or couplings in various beyond the standard model scenarios. So then this leads us to say, well, if we can't see any new physics beyond the standard model physics directly, maybe it's hiding. Maybe we can see traces of it in some standard model production process. So here's an example. I looked at the production process of a Z boson produced with the Higgs boson. That in the standard model gives you the black curve. And then we started fiddling around with the coupling of the Higgs to the Z boson, and we produced a couple of other curves. So this would be a purely standard model-like process. But if you see, instead of the black line, you see one of the other color lines, then you say, oh, I have some non-expected behavior. Maybe that's due to some new physics. And you can make the argument that if you have new physics at an energy scale higher than the production threshold at the LHC, so between 1 and a few TeV, then you can try and parameterize these new physics by some operators, which you add to the standard model Lagrangian, starting at dimension 6. A Lagrangian has to have mass dimension 4. So when I add these dimension 6 operators, they should be suppressed by some energy scale squared. And that should be the energy scale of these new physics, few TeV. And then the effect on the standard model observable is going to be something like Q squared over this new physics scale squared. Q squared should be the typical scale of the standard model interaction, which I've told you should be somewhere in the region of 100 GeV. So I have 100 GeV over a few TeV, all squared, a few percent. So once again, we get to this idea that with a few percent precision, we can not only explore the Higgs boson, but we can also see if maybe there's some new physics hiding in some inside the standard or in some standard model-like process. So this really motivates this high precision program to fully understand the mechanism of electroweak symmetry breaking and to make full use of the enormous amount of data that we have in order to try and find some sign of new physics. Okay. I should have said at the beginning, if there are any questions, please interrupt me, because I'd rather be interrupted and not get to the end than have people being completely confused. Yeah.
That's a technical question.
Yeah.
Why do the operators that we add to the standard model have to be dimension 6?
They don't. So no, it's a very good question. So standard model is dimension 4. So you could say, well, look, I know how to count, and after 4 comes 5. So why don't I add dimension 5? It turns out that you can show the dimension 5 operators only relate to the neutrino mass. So you're welcome to do it, but you won't really see any impact at the LHC. You can then add dimension 7. Dimension 7 is similar, but as soon as you go above that, you're going to have something that looks like Q squared over new physics to the power of 4, right? Or to whatever power. And so you go down from a few percent to, a few percent squared, which is like 10 to the minus 4. In certain cases, this might actually be relevant. but for the majority of cases, dimension 6 is what you need. There's another, let's say, practical problem, which is that if you write down the complete set of dimension 6 operators, which are consistent with Lorentz symmetry, there are 2,499 of them. Okay, which means that in principle, what you should do is you should do something like, that would be okay, because we have a lot of things that we can measure. So what you could imagine doing is you take all the data from the LHC, all the different production mechanisms, all the different production processes, all the different observables, and do an enormous fit of 2,500 operators. And this is what people do. And it's very important for people to do that. But of course, it becomes very unwieldy. Typically, people impose some additional symmetries like flavor symmetry to reduce this number down to about 100. When you get to higher dimensions, I don't remember what the number is, but it's much, much larger than 2,500. So then it becomes extremely difficult to actually do anything with that number without imposing some additional assumptions, which again, you can do. And if they're well motivated, then it's acceptable, but you lose some generality. Okay, so we want to make theory predictions at the percent level. And we can start off by saying, well, the question is that even possible? And at first glance, you might say, well, we could be in trouble because the LHC collides protons. So we should be looking at the strong interaction, the theory of quantum chromodynamics. But the QC Lagrangian involves quarks and gluons, not protons. Quarks and gluons are strongly coupled and confined within protons, which are composite objects. And the QC Lagrangian is not solvable. And so it's very difficult to understand the proton dynamics from first principles. So we are saved by a notion called factorization. And the idea behind factorization is that if you have phenomena at very different energy scales, then the behavior factorizes and you can treat the behavior differently. So here's a little picture of a standard of an LHC interaction. So here I have a bunch of partons, the collective name for quarks and gluons inside a proton is partons. Coming in over here, this is my proton, here's another proton, and these protons are at the energy scale of about the proton mass, so the 1 GeV. Then one of these partons, or two of these partons, undergoes some what we call hard interaction. So this interaction will be the sort of thing which produces electroweak particles, Higgs bosons, doubly bosons, or maybe even new physics. So the energy scale is much, much higher, at least 2 orders of magnitude higher, around 100 GeV to 1 TeV. And then afterwards, these particles sort of move out into the detector. They radiate off a bunch of energy, and as they lose energy, they hadronize. And then again, we're at the 1 GeV scale. So we can really treat the process, the red processes and the blue processes separately. And we can form this into a theorem. This is a misnomer. It's not really a theorem. It's only proved in very specific cases. Let's just say, let's call it a theorem because I guess there are no mathematicians in the room to shout at me. On the left-hand side, we have a physical observable, something that you can measure at the LHC. And on the right-hand side, we have this integral. The piece that I'm going to be discussing is the so-called partonic cross-section. So this is the thing that involves the fundamental particles of the standard model, quarks and gluons, electrons, doubly bosons, Higgs bosons, etc. So it's the stuff that we're most interested in. And it sits at consequently, its scale is assumed to be large, between, as I said, 100 GeV and maybe up to 1 TeV. There's a phenomenon called asymptotic freedom, which says that at this energy scale, the strong coupling actually becomes quite small, around about 0.1. And as soon as we have a small parameter, physicists go, fantastic, I can use perturbation theory, because there's really very little that we can do in physics, and perturbation theory is one. So we can use a tool called perturbative QCD. Okay, then very quickly, what are the other things in this on this right-hand side? The first two things are called parton distribution functions, PDFs, which basically tell you how the partons behave inside the protons. And again, this is at an energy scale of around about the proton mass, 1 GeV. These are not directly calculable. You extract them from data using well-understood processes like deep inelastic scattering or Drell-Yan production, etc. And of course, there's a bit of an interplay because the better you calculate those processes, the better your PDFs get. So at the moment, the precision from the PDFs is at the level between 1 and 5%, depending on a number of factors. But there's a lot of work that's going on to improve the precision with which we can determine PDFs, including at my university. So then as these partons move out from the hard process towards the detector, they radiate off a bunch of stuff. They like an electron that's being accelerated, it's going to radiate off stuff. This is exactly the same. The problem is that the theoretical interpretation or the theoretical description of this, perturbative QCD, at least in some regions of phase space, starts to become difficult because you get very large logarithms that spoil the perturbative convergence. And you need to deal with these logarithms. You have two ways of doing it. There's an analytic procedure called resummation and a numerical Monte Carlo procedure called parton showers. As you may expect, the analytical procedure gives you much more control. It's much more precise, but it's not very general. You typically need to do a resummation for a particular process and a particular observable. Whereas the parton showers are much more general, so you can typically do that for a whole class of processes or a whole class of observables, often all possible observables. But they're far less precise and they give you less control. It's much harder to understand the uncertainty associated. This factorization isn't exact. There are non-perturbative effects which are power suppressed, and they come in with the scale of the confinement scale, lambda QCD, divided by Q. This Q should be the smallest scale in your hard interaction, so typically around about 10 GeV. And so you can see that these effects are at the level of around about 1%. N should be some integer number starting at 1. It's still an open question what the value of n is, but even if n is equal to 1, then you get a few percent correction. If n is equal to 2, then they're even more suppressed and we're even happier. So what I try to show you is that, at least in principle, it's possible to get this percent level control on your theoretical predictions. But of course, it's difficult. Just because it's possible doesn't mean it's easy, and it requires a lot of work, really on all fronts. So the determination of PDFs, the fixed order calculations for the hard process, resummation techniques, parton showering algorithms, hadronization models, and so forth. And you can, and people do, spend an entire career working on just one of these areas. And I don't think there's anybody in the world who's an expert in more than 3 of them. And that's being kind of generous. So today I'm going to discuss fixed order calculation. Okay, so we can do a perturbative expansion in the strong and electroweak couplings. The strong coupling is about 0.1, the electroweak about an order of magnitude smaller. And so we can write our partonic cross-section as a leading order term. Then we add some QCD interactions. We get a correction, the next to leading order correction, which is about 10%. So suppressed by a factor of 10. We add 1 order higher, so 2 QCD interactions. That's next to the next leading order, about a 1% correction, and so on. And then we can add a purely electroweak correction, so where we add electroweak interactions, that's around about a 1% correction. We can add mixed QC electroweak, which is even smaller. These are rough orders of magnitude estimate. For certain processes, they can be much larger and occasionally much smaller. So you can see that if we want to go to percent level, the next to leading order QCD and next to leading order electroweak calculations are absolutely essential. And 1 order higher in blue is necessary for certain simple processes, but not for the majority of processes. Okay, yeah.
It's having trouble keeping track of scale.
Yeah.
It's alpha strong 0.1. What scale?
So here I'm talking at the electroweak scale.
Okay.
So I'm now always discussing the stuff in red from now on, and this is always at least at the electroweak scale. I think, and so alpha S is like 0.118 at the Z mass. 91 GeV, but I think even if you run it down to about 20 GeV, you're still in the perturbative regime. You're still at about 0.1 something at that point. It's really only once you get below about 5-ish GeV that you start getting into trouble. So almost all the processes that we deal with, the scale is over 20 GeV. So this is broadly applicable. It's almost sort of applicable by construction, because we define the hard regime to be a regime in which this is true. Now, of course, there's a slight, there is another trick, because this runs in the opposite direction. So as I go to larger energies, the electroweak coupling gets larger and larger. But at the LHC, I never get close to the Landau pulse. Right? So this is always perturbative, even if you go up to the highest events you can get at the LHC. This is still relatively small. There are caveats to what I'm saying, but broadly speaking, this is true. Okay, so how do we actually calculate these things? Well, first we have to calculate something called a matrix element, and that you can think of as just like an amplitude in quantum mechanics for going between some initial and some final state. And so like in quantum mechanics, if I take the matrix element and square it, I understand this as some probability. I then need to, this is for some given set of momenta in the final state, and I then need to integrate over all the possible momenta of the final state particles, and that I've now taken a probability and essentially summed over all possible final states, and I can, that is called a cross section, and that is related to the number of events that the experimenters are actually going to measure. Okay, so how do I compute QCD corrections? So in black, I have the leading order process, and I have to add in QCD radiation. And that radiation can take two forms. In the first one, I have a virtual gluon between these two legs. So this is what we call a virtual correction. The momentum of this gluon is completely unconstrained, so I have to integrate over all possible values of its full momentum. It's a virtual particle, it's not directly observable. You never see it in a detector. I can also have real corrections. So here I radiate off an on-shell gluon, meaning its full momentum squared is equal to its mass squared, in this case 0. And this is observable. This can be actually seen. Gluon isn't directly observable, but you can see something like this in the detector. For the experts, it radiates and becomes jets and hadronizes, and you can see it. And so these two diagrams really encapsulate the difficulties of computing the corrections beyond leading order. The first is computing the integrals for these virtual amplitudes, because I have to integrate over the gluon's full momentum. And this is easy to understand. Integration is difficult, and not only that, this integration is actually divergent. There are multiple singular regions that you have to integrate over. And that's a problem, because if you tell me, look, I have an integral to do, and I know it's convergent, I say, okay, fantastic, I'll throw it on a computer and make the computer compute it numerically. But because this thing is divergent, if you want to do that, the computer is going to give you a very, very, very big number, essentially infinity. If you want to do this, you have to first find those singular regions and get rid of them.
In the second diagram, are we just setting the momentum to 0 or the square momentum?
Square, the square. So it's full momentum square.
Because doesn't that make it like a different process if you're considering another particle? You're considering an entirely different.
It's a fantastic question. Can I get back to that in 2 or 3 slides? But that's exactly the point, right? It isn't the different process, and I'll show you why in a moment. Okay, and it's connected because it's connected to the second point that I really want to discuss, which is the treatment of infrared divergences. So let me look more carefully at this diagram over here, and in particular, let me look at this propagator over here before the gluon. Now, I don't know how well you guys all know quantum field theory, but it turns out that this propagator, if you just look at the denominator, you get something that is inversely proportional to the energy of this gluon and the angle that is made by the 3 momenta of the gluon and the parton. So you can see if I take the energy of the gluon to be 0, which I call the soft limit, or if I take the angle between the gluon and the parton to be 0, which I call the collinear limit, then this propagator is going to become singular. And that's a problem because remember, this propagator is going to sit in my matrix element squared. And remember, I said I need to integrate this over the entire phase space of this gluon. And that phase space is going to include points at which the gluon is soft, which its energy goes to zero, and in which it's emitted in a collinear direction. And so then I'm going to get an integral that diverges because of the soft and collinear radiation. Now, it turns out that you get, if you compute the virtual amplitude, you get similar divergences, similar infrared divergences. If we work in dimensional regularization, so we have we work in 4 minus 2 epsilon dimensions, then these divergences appear as poles in 1 over epsilon. And in fact, these can be predicted. There are known formulas up to 2 loops telling us what these divergences are in the virtual amplitude. Now, divergences in physics tell us that we're doing something wrong. They usually assign that we're applying a theory in a place or scenario, if you prefer, where the theory is not applicable. And so you might say, well, why should I have divergences here? Is my theory sick? And the answer is no, there's nothing wrong with the theory. It's just that this separation into real and virtual, this makes a lot of sense to us. This is coming back to your question. This is a very intuitive way of us to think about it, but it's completely unnatural. There's nothing in nature that tells you that I have to split real and virtual. And so this tells you that when you combine the two, they have to the singularities have to cancel, giving you an infrared finite physical result that you can go and measure. So if you like this, to answer your question, these are entirely unphysical divergences, and what they tell you is that these two things are actually connected. The real and the virtual corrections are connected. They're not separate. So it doesn't make sense for somebody, it makes perfect sense to talk about a next leading order correction that is 10%. But it doesn't make any sense to talk about a real correction or a virtual correction. Those are not well defined in quantum mechanics. If you like, what I can say is that these are the same order in a perturbative expansion. So the fact that sometimes it's real and sometimes it's virtual, there's nothing I can do about it. And they're connected through the infrared poles. Okay. How much time do I have left? 15 minutes. 15 minutes. So then you say, okay, well, what's the problem? I do this integration, I get the singularities, I cancel them with the virtual, and I get something finite, and I'm very happy. The problem is that if I only get this integration after I integrate over the phase space of this gluon. And as soon as I do this integration, I lose some information about the gluon. Which means that if an experimentalist comes to me and says, look, I think that, can you tell me how many events, what percentage of the events would have a jet transverse momentum above 50 GeV? I don't know, because I've integrated over this gluon, I've lost all the information. There's nothing wrong with it, absolutely nothing wrong with it. It's just that you'd like to have as much information as possible that you can compare with experimental data. Since the data is there, and since we've spent billions and billions of euros getting it, we may as well make full use of it. Okay. So what we'd like to do is develop something which we call a subtraction scheme, which allows us to extract these singularities without performing the integration over the full phase space of the radiated part-time. This will allow us to see these singularities as poles in 1 over epsilon. So we'll have poles in 1 over epsilon from the real, poles in 1 over epsilon from the virtual. We bring them together, we cancel them, and we get something that is finite, manifestly finite. And the basic idea is, let me imagine that I have some integral over here which is divergent. So this matrix element squared becomes singular in some regions, soft and collinear regions. Now imagine I can find a function S which reproduces the matrix element in these so-called infrared limits. And let me subtract this S from the integrand. Then I have something that is manifestly finite. After all, every time I hit a singular region in the matrix element squared, I remove that singularity by S. By construction, that's what S does. Then since this is a convergent integral, I don't need to integrate it in d dimensions. I can integrate it in 4 dimensions because I know there are going to be no singularities. And that means that's great. It's a convergent integral. I can put this into a Monte Carlo program and I don't need to worry about it anymore. Practically speaking, I spent a lot of my time writing this Monte Carlo program, but for the purposes of this discussion, we don't need to worry about it anymore. And then we have to add then we've subtracted this function S, we need to add it back. And here we integrate over the full phase space, and this in d dimensions, and this gives us the singularities as poles in 1 over epsilon. Well, with these poles, we can then cancel them against the virtual correction.
Sorry.
Yeah.
Maybe a basic question.
Sure.
So how do you know such a function S always exists?
Ah, very good. Yeah. Okay. So the problem is finding S. And I'm gonna, hopefully I'll have time to explain why it's different, why it's, how we can do it. So there's a very important property of QCD, which is that the amplitude is factorized in the soft and collinear limits. So if I take this process and I take the soft gluon, this is proportional to an iconal function, we'll get back to that later, multiplied by the same matrix element with no gluon whatsoever. The iconal function depends on the momentum of this gluon, which is now this P with this sort of funny M, as well as the color charges of all the other partons, and I sum over all possible partons. But the important point is that the gluon dynamics are, it factorizes. There's no gluon dynamics here. It's only, all its dynamics are sitting in this function. And similarly, if I take a collinear limit, I get something called a splitting function, which is a function of Z, which is some ratio of energies, including gluon energy, again, multiplied by some leading order stuff that is completely independent of the gluon dynamics. So this means I can construct the subtraction terms directly from the soft limit, from the limits. So this answers your question. So all I need to do is I identify this function S with one of these, either soft or collinear, depending on which scenario I'm in, and then I have exactly what I need. I can subtract and integrate this in 4 dimensions because it's finite, and then all I need to do is to integrate this counter term. And because this the unresolved gluon has decoupled, either decoupled because of this factorization, I can perform that integral. In other words, if I integrate this thing, this whole thing on the right-hand side, over the phase space of the gluon, this has no dependence on the phase space of the gluon. I can take it out of the integral, and then all I need to do is integrate the iconal. And since I know the expression for the iconal, I can integrate. It turns out not to be a difficult integral. You get some Euler beta functions. And then you can combine them with the poles from the virtual amplitude, which, as I said, are already known from an incredibly neat paper from 1996 by Catani. And you cancel the singularities, and you can then take the limit where epsilon goes to 0, and you get a finite fraction.
Another small question.
Yeah.
So you're doing dimensional regularization.
Yeah.
Out of all of this, even once you have all of this, fine, maybe gotten rid of your singularities. But when you do dimensional regularization, you have to introduce a scale.
Yeah. So
where is it, and what do you do with it?
So it turns, so you basically do the dimensional regularization for the UV and infrared at the same time. So you do introduce a scale. It's called a factorization scale, and so you will have some dependence on the factorization scale in your final result, as well as the renormalization scale from renormalizing QC. And in fact, this is so formally. It's just like with the renormalization scale, there's a renormalization group equation, which tells you that there should be no dependence on the scale if you sum to all possible orders. And in fact, what we do is we vary these scales as some estimate of the missing higher order corrections.
So it's varied by a factor of 2, right?
Yeah.
Why?
Purely conventional.
And how do you think of that as an uncertainty?
Okay, very good. This is a
Cole's question.
yeah. This is an enormous can of worms. So okay, how to answer this? Okay, so I think the best way to explain it is a historical approach. That this idea came around 30 plus years ago, when typically most calculations were in next leading order. The uncertainties were at the level of 10%, maybe 20%. And so, and similarly with the experimental measurements. And so you didn't need a particularly good estimate of the theoretical uncertainty. So you could more or less do the first thing, that the easiest thing that came to mind, and it's very easy to run your code once and then 2 and 3 times and look at the scale variation. I think this is, so I think, and this is, I think, becoming a more and more popular opinion, this is not an adequate estimation of the scale of the uncertainty due to missing higher order corrections at the moment. The problem is coming up with a better one. Okay, and it's really unclear how to do this. for a couple of reasons. There's sort of a physics reason and there's a sociological one. The physics reason is that what you're essentially doing with the scale is you're trying to understand the logarithms that are appearing at higher orders. And so a colleague of mine put it very well that you basically play whack-a-mole with the scales. So you can choose some functional form for the scale choice. If you do a dynamic scale, you can choose some functional form that minimizes some of the logs, but other logs will be large. And then if you change the functional form, you might make these logs small, but your mole appears somewhere else. So there's really nothing you can do, right, in order to pick a good scale, right? It's not clear how to define a good scale, a correct scale choice. It's also not clear how to vary these. That's the physics reason. The sociological reason is that at the moment, to come up with, okay, so the cutting edge now is N and alone. Recently, about 2 years ago, people computed 3-jet production at next leading order. Formerly it was leading color, but let's just say it was 3-jet production. This took 100 million CPU hours to run. Okay, now if you're going to run something for 100 million CPU hours, and then somebody comes to you and says, look, I would like you to rerun it for a whole bunch of different scales, you can imagine what you're going to tell it, right? It's not going to be polite. And this is what I mean, the sociological reason, that people take years and years to do these calculations. And once you get the final answer, quite frankly, you're sick of the whole thing and you just want to write the paper. And then it's very easy to say, okay, yeah, we do a factor of, we vary by a factor of 2 and interpret that. And I don't know how to combat this, because this also relates to the fact that, you're talking about timescales that are now 2 to 3 years, which is a time scale of a postdoc or a PhD position. And it's fine for somebody who has a permanent position. But if you tell your student, look, we can't publish this paper for another year because we have to do a good estimation of the theoretical uncertainty, which means you're going to have to apply for a postdoc without a publication, that's not a very nice thing. So this is what I mean by a sociological reasons. If you want my personal opinion, the way to do it is you have to kind of split the papers in two. You have to have, if I say I do an N and a low calculation for a particular process, there should be one paper where I basically give the result and a very rough estimate of the theoretical uncertainty, and then a follow-up paper where I do a more in-depth investigation of the theoretical uncertainty. In my mind, this is entirely justified in terms of the work. But of course, this takes a while before the community gets used to it. And now if I do that, if I write a paper with the results and then write another paper just exploring the theoretical uncertainty, I know that the referee is going to reject. So this is what I mean. You kind of need a sort of a shift in mentality. And again, as I said, this becomes a sociological problem. I think people started thinking about this maybe 3 or 4 years ago. Last summer, I was at a workshop in Aspen and people raised this point, and I expected people to be very opposed to it. And most people were of, let's say, broadly speaking, my opinion. Not with how you need to do it, but the fact that something needs to change. But as you know, I mean, this is a theoretical community. Everybody will pull and push in their own direction, and it'll take a long time for there to be some consensus. But I think, as opposed to maybe 10 years ago, people said, look, this factor of 2 estimation is absolutely acceptable. I think now people are realizing that this is just not, we're spending so much time coming up with things that are accurate to within a few percent. And then to do this essentially, glorified thumb suck for the uncertainty is not acceptable anymore. Those are the answer. But the problem is that there's been no good suggestion and easy to adopt, right? Because I can very easily run my code 3 times.
Maybe just a follow-up to that question. I mean, as you said, there's been a lot of calculations to many orders. So, I mean, I could imagine, if you apply this prescription on the factors of 2 at leading order, and then you actually look at the result and you do next leading order.
Yeah.
Is that within the realm? Like, I guess you can
Very good,
estimate how.
very good question. Strongly depends. Strongly depends on the process. And this is part of the problem. So, sorry?
That's scary. Yeah.
Yeah, exactly. So for example, you take the 2 simplest processes that you have. One is Higgs production. The other one is gluon. They're simple because they're essentially 2 partons coming in, gluon or quark anti-quark, one's color singlet going up. Either It's called a photon for Drelion in the first approximation, or a Higgs boson. Drelion beautifully convergent. Okay, at least up to n-n-LO. So leading order scale uncertainty is about 10%, maybe 20%. Next leading order correction about 10%. So you can really make a plot where you have something like a band. This will be leading order. This is the next to leading order, and then there's the n-n-LO. So each band represents a scale uncertainty, and so you have this lovely, beautifully converging series. Do this with Higgs production, it's completely wrong. Okay, so the Higgs production at leading order, the uncertainties are about maybe 20%. The correction is a factor of 2. It's completely incorrect. You look at next to leading order, the corrections are about 1.5-ish. The perturbative series only stabilizes after n-n-LO. Now I know exactly why it's the case. It's essentially a statement that gluons have a larger color charge, so they radiate more than. That's the reason. So there's a good physics reason behind it. It's not a mystery. But this is the problem that you don't. So you sort of start off with this knowledge. You don't feed it into your scale uncertainty, right? So the correct thing to do would be to say, okay, somehow my scale uncertainty should take into account the fact that I've got quarks or gluons in my initial state. Or you have new channels that open up, new photonic channels that open up at higher orders, which are not taken into account by this very simple process. And then, we've also seen very strange things. So I looked at it. I'm getting completely off topic, but I don't care. So I looked at a process called VBF, vector boson fusion production of a Higgs. So you have two quarks coming in, they exchange a W and Z boson. This W and Z boson radiates off a Higgs. It's more vector boson fusion. And we looked at this where the Higgs decays into BB bar. This is a very nice way of trying to measure the coupling of the Higgs to the B quarks. It's particularly nice because these are typically back-to-back jets, so you sort of have these two things coming in. They kind of do this, so you have them in the very forward region of the detector, and the Higgs is in the central region of the detector. So when you radiate off this BB bar, there's very little else over there. So you see this BB bar, and you can reconstruct the Higgs. So from an experimental perspective, this is very nice. So we looked at this, and we did, and you look at VBF, and this is very well known perturbatively. So this is known at next to leading order. And the corrections are about 1 to 2%. Let's say 2%. Very, very nicely converging series. Okay, great. Now you start saying, let me add in the Higgs decays to BB bar at the same order. And I forget exactly what the numbers were, but they were wildly different from the scale uncertainty. Okay. We were able to understand the reason, and it's to do with the particular cuts that the experiments do on these BB bar pairs. And I think that it's a bit complicated and I can't show it, but I think what we're really doing is we're introducing large logarithms, which are spoiling the perturbative convergence. But again, in an ideal world, as soon as you do this and impose these sort of cuts, even at a lower order, your prescription for estimating your uncertainty should take this into account, and it doesn't. So so you opened up a can of worms, I'm afraid. Okay,
but it's an important one.
Yeah, it's a very important one, but it's really something. As I said, I think there's a pretty maybe not universal, but I would say majority opinion of people who do this would say that what we do at the moment is not sufficient. And I think that I would say nobody is confident in any idea that they have. That's not true. There are some people who are very confident in their, even though the ideas are not good, in my opinion. But let's say I wouldn't say there's anything where anybody can say, oh, that's a good idea, even if I disagree with it. So for example, there are other subtraction schemes, that are competing with the one that I work on. And even though I think that mine is the best by definition, I recognize the other ones as being good ideas. They have some interesting physics behind that. I don't think we're there yet for something like this. I'm now way over time. I can carry on. As I said, I know I'm standing in between people and the long weekend. So if you want me to shut up, I'm happy to do so.
So how many slides do you have?
I think I have about 50-ish. Let's say if I can get to, but maybe I just say a little bit more. If I can go for another 10 minutes, is that fine?
Yeah, and maybe if you could have like a particular calculation where you talk to either higher orders.
Yeah, okay. Let me see if I can get there by. Yeah, if you need to go, I mean go, because I promise you I won't be offended. Okay. So the subtraction at next leading order is fully solved, and it has been since the mid-90s. And the schemes are very nice. They're fully analytic, means I have an analytic computation of the counter term. They're fully local, and they're fully general. So I can apply this for any process at the Large Hadron Collider. And these are, so this is a very nice setup. If we go one order higher at next to leading order, now we have to have two real emissions, the so-called double real. And there's a problem with constructing a subtraction term for this, which is that the singularities overlap. And in order to get around this, there have been a lot of approaches that have been proposed over the last 20 years or so. And in the last 10 years or so, they sort of reached the maturity level that they could be used for N and low accurate predictions. And there's really been an explosion of these in the last 10 years. However, none of these methods are at the same level as we have at next leading order, meaning they're fully local, fully analytic, and applicable to any process at the Large Hadron Collider. And developing these methods is an active area of research. And this morning, we put a paper on the archive on exactly this topic, and not only us, but one of our competitors put a paper out on their method. So as an illustration of how active it is, we get two papers in one day. Okay, yeah, let's see if I can say something about this. Okay, so the method that I've been working on for the last 8 or 9 years is called the nested soft collinear subtraction scheme. It's based on an idea called color coherence, which says that there's essentially no interplay between soft and collinear limits. And so from a subtraction point of view, I can treat them independently. So there's no overlap between soft and collinear. I can regularize them entirely or subtract them entirely independently. There is some overlap in the collinear singularities, and this we can separate using basically pulling apart the phase space using things called partitions and sectors. And then once I've done that, I can basically do exactly what I did previously. I could just construct the subtraction terms from the limits. It's a method that's fully local and fully analytic. We were able to write some fairly efficient numerical codes based on it, albeit for very simple processes. It's very flexible. We adapted it for mixed QC electroweak corrections with not much effort. And so we can say this is a nice idea, and we generalize. And this is what we've been doing over the last 3 or so years, trying to write down a completely general solution for it. The idea in brief is go back to next to leading order and try and identify singularity structures that appear. So let's imagine I can put all of the singularities that come from soft radiation in some function, which I call IS. I put all of the virtuals in another function called IV, and all of the singularities coming from the collinear radiation in another one called IC. And I can then show that when I take the sum of these, I get some total number, IT, which is finite in epsilon. And then what I want to do is I do my next to next leading order calculation, and I try and find the same structures appearing. And I can do that. This is a situation where you have a double soft. So both of the radiated gluons become soft. And you see I have an IS squared and something that's related to an IS with some tilde. This is a soft limit applied to a real virtual. And here you can see I both have a soft limit and a virtual, or a soft, or an IS tilde. And so you can proceed through all the counter terms that we construct at next to next leading order and pick out all these individual terms. So when we look at the final next leading order result, we're able to reconstruct these ITs. And as soon as I see this IT, I know, okay, that is finite, because I've seen already that this thing is by definition a finite quantity. So I don't have to So this sort of shows this translation of poles kind of implicitly because it's hidden inside there. Now there's still some stuff in the dots that you have to show by brute force calculation that things cancel. But the cancellation of the poles is made similar because many of these singularities are captured already within these finite quantities IT. This is opposed to a brute force way. The brute force way is you just sort of compute all these things. You basically throw them into Mathematica, and you get Mathematica notebooks which are several megabytes, and that take about an hour to evaluate to essentially show that the poles all cancel because you have these very huge expressions. You can do this. It's time consuming, it's inefficient, but this is why we have graduate students. But after a while, even the graduate students start to get annoyed, and you start to think maybe there's a more efficient way of doing it, and it turns out that you can do it. And then instead of, because you've put a lot of these poles are sitting in, or the cancellation is sitting inside these quantities, the stuff that's left over is much, much neater. Which is how we were able to write down a method that has for quark anti-quark annihilation to n gluons. So n is really an arbitrary parameter. Any number of gluons you like, we can do it. We were able to show the pole cancellation and have fairly compact finite formulas. And by compact, I basically mean we have a sum that runs from 1 to n. Okay, if you want n to be very large, of course, this is going to be a very large sum. There's nothing I can do about that. But you know, as an expression, it's fairly easy. And of course, as a Monte Carlo code, it's incredibly simple. I write one function with a parameter n. That's all I need. Now this is a very nice situation because you have this very, very symmetric final state, right? I can essentially permute any of the gluons, and all I pay is well, some permutation factor. So we said, okay, well, what happens if we kind of start to break this the symmetry and we introduce a final state quark? And we were able to show that these methods are, broadly speaking, still applicable, even when you don't have a fully symmetric final state. That was the paper that came out this morning. Again, we're able to show the cancellation of poles for an arbitrary number of gluons and one quark in the final state, and derive finite formulas. And in fact, we can see that to a large extent, the cancellation of poles factorizes on each and every. So basically, for every final state particle, there is some cancellation of poles. So you can add as many as you like, and you basically just cancel with every additional real radiation. There's a cancellation on that particle. Now, of course, what you need to do is you can say, well, let me go to an arbitrary initial state and have now an arbitrary number of quarks of the final state. But really, all the physics is sitting in one of these two. The remaining obstacles are just the combinatorics of having to deal with different flavors of quarks in the final state. Essentially, it's bookkeeping. It's difficult, it's painful, but conceptually, it's the same. I don't think there's any new physics concepts that we need to come up with in order to write down a fully general method. Okay, so with this, I will just leave the conclusions up there. As I said, I think we've had a good discussion, but I'm very happy to have more questions. I have about 20 backup slides if you want the gory details. I'm very happy to go into them. If they're more general questions, I'm happy to talk about them. Oh, but before I maybe do the questions first and then say something, Andre? Okay, so if there are any questions, then yeah.
Okay. Any further?
Yeah, so Andre asked me just to say a few words about coming from Cape Town, doing my undergraduate and master's degrees here, and then going overseas for my PhD. So I'm happy to say a few words, but I think we said we do the physics questions first, if that's fine. So if you're interested in that, then you can also stick around here.
In the diagram you had of the hard to soft, one for green and blue and red.
Okay,
I'm seeing a small location where might be new physics.
Oh, okay. Yeah.
What is the purple pancake?
Purple pancake. Oh, okay. I haven't been asked that question before. So this represents so-called double parton interactions. So usually you would have two one parton from each proton that come together and interact. In here, you have multiple partons that happen, so 2 from this one and 2 from that one. They're also at a fairly soft scale. You can think about them as they are kind of a correction to the parton distribution functions. I think if there are any people who work on either double parton scattering or parton distribution functions, they'll, throw a tomato at me if I say that, but roughly speaking, you can think about it. I didn't even realize there was a purple pancake. I didn't make the plot. It's I don't know who made that. I should really credit it.
That's a lot going on there. Yeah, further questions?
When you call it this infrared divergence problem, why do you say infrared?
So it's because it's really because of the soft limit. So the idea that the blue one becomes soft, so it has low energy, large wavelength, and therefore is infrared. It's a bit of an abusive notation because the collinear limits are not infrared. So it's sort of people used to say soft or infrared and collinear. But after that just becomes a mouthful. So now infrared is just, as I said, there's a slight abuse of terminology. We mean soft and collinear, and it comes from the name.
Anything that's not UV, right?
Yeah, exactly. So as opposed to the ultraviolet divergences, which still exist, but they are, so in my mind, ultraviolet divergences are not a problem because there's renormalization. It's a problem, but it's a problem that some geniuses 50 years ago solved. They got the Nobel Prize, and now it's not a problem. In my mind, I know how to renormalize QCD. If I'm working with an effective field theory, then this is not renormalizable, and then it becomes a problem. I have to renormalize order by order, which is painful. But since I don't have to worry.
Maybe Ben and then Bruce.
So you had this subtraction method where you're integrating some matrix element, and then you had this S term. So at the end of the day, that term on the far left is still divergent. Is that ultimately not what you're trying to calculate?
Yeah, it is. So the point is that this term is still divergent, but this is only part of the thing I need to calculate. This is only this real correction. I also need to add the virtual correction. The virtual correction also has poles in 1 over epsilon. So I get poles directly from the matrix element for the virtual correction. I then get poles from this term. I add them together and they cancel.
So we just need to calculate this first term on the right hand side.
You need to calculate both of them because okay, so yeah, so importantly, this gives you essentially a Laurent expansion in 1 over epsilon. At next leading order, it starts at 1 over epsilon squared, next leading order 1 over epsilon to the 4, etc. Once you cancel this with the virtual correction, you're still left with epsilon to the 0 term, so finite terms. So you still get something in here. You still get a non-zero contribution in there because you get order epsilon to the 0. You take epsilon to 0, these terms are.
I mean, is this S term on the far right? That must be divergent.
It is divergent because it has poles in 1 over epsilon.
Yeah.
So if I take epsilon to, so it's a question of order of operations. If I take epsilon to 0, this thing diverges, and I'm unhappy, and so does the virtual amplitude. What I need to do is add them, but this is what I was saying in response to the question earlier. That is not a well-defined thing because there's a virtual or a real correction by itself has no physical meaning. Only the sum has a meaning. When I take the sum, I see that the poles cancel out. Then I have something that is purely epsilon finite. I take the limit epsilon goes to 0, and I have something that is finite. But importantly, so of course I can always, there's nobody tells me what exactly the form of S needs to be, right? So all it needs to do is obey these two conditions. So I can have a function S, you have a function S tilde, and we compute these, and we will get the same poles because the IR behavior has to be identical. That's the condition, but the finite piece will be different. So what is in your Monte Carlo will be different. It'll be minus S tilde, and your counter term will be different, but the sum will be the same. And actually, this is a nice way of trying to check it. Basically, you want to introduce some parameter here, which we call, for historical reasons, alpha parameters, which essentially change the form. Not strictly speaking true. They change this S. And then you compute essentially this thing in your Monte Carlo code. You have a parameter alpha, and then you have some functional dependence on alpha in this thing. So then I run my code for alpha should be between, let's say, 0 and 1. I do it for 10 to the minus 2, 10 to the minus 1. If I get the same number, then I know I've computed my counter terms correctly. And what's even more surprising, I haven't made any mistakes in my Monte Carlo.
Just to go through it again, you do this for each of the correction. Right.
We say each of the corrections.
So for the real and virtual, right? You wanna do a procedure, make a procedure like that? Or?
So for the virtual, I actually don't need to. So the virtual, there are known formulas. In fact, I have this in one of my
I'm
last.
trying to find out where a finite quantity comes out. Yeah.
Okay. So here, so this is the expression for the virtual poles from this paper of Catania. So basically, if I do a Laurent expansion of this thing, this has arbitrarily many partons and some dot product of some color matrices. This gives me all the infrared poles at one loop for any process. Okay. For all I have to do is know what the external partons are. So basically, if I have something like a one loop matrix element, I can write this as follows. So this is where all my infrared singularities are. So this is poles like 1 over epsilon squared. This is the leading order, or the stuff without the loop. And then I have some finite quantity. Now this finite quantity is process dependent. So I have to compute it. But this sort of is difficult, but this is a sort of a separate problem. So in as far as I'm concerned, to show the pole translation, all I need is this. I then say somebody else needs to supply me with the finite piece. It's not my problem. At one loop, it's fairly simple to do it. At 2 loops, it can be anywhere between difficult and very, very difficult. And if it's very, very difficult, then I have a fantastic solution, which is I call up one of my friends and I say, can you please compute a 2-loop amplitude for me? And I'll do the subtractions.
In your one expression of proper values and stuff, so the diagrammatics.
Yeah.
Yeah. In the whole expression, I'm just wondering, are there overlapping divergences contained?
In this one?
As your V singular suggests, because you have a 1 over epsilon.
Okay, but it's to the power of epsilon.
Yeah, but you have one of the factors is the V singular on the right hand side, which has
Yes.
1 over epsilon square.
Yes.
And this seems to be an indicator of an overlapping divergence.
Why is this? I mean, yes, there are overlapping divergences, but why is this an indicator of it?
You know, 1 over epsilon from soft, 1 over epsilon from clear.
Oh, yes, absolutely. So yes,
Because the rest of it doesn't look like having overlapping divergences. So all of that is condensed in the singular.
Yeah. At one loop, and it's particularly easy at one loop. It becomes this is all one loop. So there's a similar, more complicated, but not much more complicated formula at 2 loops.
1 loop plus virtual.
So 1 loop virtual.
Okay. And since you tried to sell us the feeling that your method is perhaps a candidate of being a general scheme.
Yeah.
Are you claiming, and then the next step would be next order.
Mm-hmm.
Are you confident that the question of overlapping divergences can be kicked off at some point?
At next linear order, yes, absolutely. So at 1 order higher, I have no idea. 1 order higher, there's no local subtraction scheme. At 1 order higher, people do things called slicing, which might be adequate. There are huge problems with constructing a subtraction scheme at n cubed or low. For a start, this is where if I go back to my factorization, it's not known what these factors are, and in fact, it's known that collinear factorization is broken at n cubed low. Okay, there was some idea that this might even break the PDF factorization. There's now some work by Neubert Becker and some of their collaborators, which said maybe it's not the case. This is, I would still say, is an open question, although things seem to be going in the right direction, that we're not going to break PDF factorization, but we know that collinear factorization is going to be broken. So it's not even, it's unclear how we would even approach this, at least in my mind. There are some ways that maybe you could do it approximately, but this would be very difficult. About the issue of overlapping divergences. So it depends on what you mean by solve. In the following sense. So so since you asked, I'm now going to, you've also opened a can of worms, which is this idea of color coherence. So the idea of color coherence is, imagine I have a parton traveling along, a quark traveling along, and it emits a soft gluon. And then it undergoes a whole bunch of collinear split. Now this soft gluon, because it's soft, it has a large wavelength, it can't resolve the details of this collinear splitting. It only sees the total momentum and color charge. And this is basically what all parton showers have at their heart. It's not usually shown I mean, it's there in most subtraction schemes, but it's not kind of front and center. And we said, okay, let's put it front and center. And basically it tells you that I can treat all the soft singularities first. There's no overlap between soft and collinear. I treat all, I pretend that there are no collinear singularities. I subtract all my soft stuff. And then I say, okay, now I have to remember, aha, they're collinear singularities. I subtract all of those. There's still overlaps between the collinear singularities, and this is what we use the phase-space partitioning and sectoring. Now, so phase-space partitioning and sectoring basically tells you I just take my multi-dimensional phase space and I pull it apart until every single part only has one singularity. Now, of course, this is something we do for our convenience because we're too stupid to integrate two overlapping singularities at the same time. But it's not what nature needs to do. Nature is infinitely smarter than me. So nature doesn't need to do this pulling stuff apart. It just integrates. Or who knows what it does. Certainly it doesn't need to do the sectoring. So what we actually saw when we did this is that we saw when we recombined the sectors after integration, when we first started developing this, we saw significant simplifications. In particular, we saw that we were able to reconstruct various physical quantities like anomalous dimensions. So we would see in this sector, we have sort of part of an anomalous dimension. In this one, we have another part. If you add them together, you get the anomalous dimension. And really, one of the things that we started doing recently is sort of saying we basically, instead of combining the sectors after integration, we combine them before integration. And then you sort of see these anomalous dimensions kind of falling out. And it's a little bit, so I don't think I have an expression for, oh yeah, so here's, for instance, this IC, what this IC is actually equal to. And you can see this is the, so it's basically a sum of some things over epsilon. And that those things all include this is the anomalous dimension of either the quark or the gluon, whatever you have, plus some logarithms, that's this Li, multiplied by the Casimirs to order epsilon to the 0. So the Ti squared is the Casimir of the parton. So it's a very.
It comes with a 1 over epsilon factor? Or?
Yes, because it's a collinear.
Oh, okay.
Yeah. So it's a very nice physical thing. And this is sort of what, if you go back to this thing from Catani, that's exactly what Catani was telling us. He's saying, look, all your poles have to, roughly speaking, look like either Casimir for the soft or an anomalous dimension for the soft collinear. And so what we said is, okay, if we look at our soft, indeed, we get something color correlated, just like Catani told us, 1 over epsilon squared. And then for the collinear, it should have some anomalous dimension. And when we put these sectors together before integrating, this is what we get. So this is what I mean by, I don't know, it depends on what you mean by solve. So it's solved in the sense that we know how to do it, and we know how to recover physical things afterwards. On the other hand, some of my colleagues might say, or competitors might say that, look, this is entirely artificial. You don't need to do this. You shouldn't be partitioning or sectoring at all. In that case, there are other approaches like the antenna subtractions that don't use this. They have their own problems, but you can avoid this. But one way or the other, essentially all these methods that I listed all the way back, God knows where, you know, they all just take, yeah, all of these methods just have a slightly different way of treating the overlapping singularities. That's the only difference. And again, which one you prefer is partly a matter of what you can achieve and partly a matter of taste. So the two at the top, I would say, are the most mature ones. These are the ones. So Stripper, for example, was used for the 3-jet calculation, and Tenor has been used for you know, a whole bunch of things. And then the other ones, in particular, the next next 4 on the list are under. Well, okay, sorry, colorful, nested, and local are all the ones that are under active development. This projection to Born is a wonderful idea, but is very, very limited because you need a lot of analytic results for the processes beforehand. And then this geometric, I think, is, I mean, I don't know what France is doing about it, but as far as I'm concerned, it's more or less dead. I haven't, there was one paper about it 7 years ago, and I haven't heard anything since. I don't know if it's still under active development. So this is, I'm not sure what he's doing about it.
Maurice had a question.
That was maybe a longer answer than you wanted.
Yeah, so just maybe a bit of a broad overview question. You're looking at these, maybe I misunderstood, but you're looking at all these different subtraction schemes.
I'm just looking at one. I mean, so what I'm saying is this is what other people are doing, trying to show you that it's a, you know, a very, very active field. And the fact that it's active also tells you that nobody, you know, when somebody comes up with an idea that everybody recognizes as the best idea, then people stop working on it. People just say, okay, that's the way to do it, we'll do it. The fact that there's so many people working on it tells you that nobody feels that way about anybody else's. My personal opinion is none of these, including mine, is the perfect thing. Okay, there are certainly problems with what we are doing. I know what the strengths and weaknesses of all of these are. We all have strengths, we all have weaknesses. I don't think anybody is claiming to have the perfect one. Whereas at next to leading order, there's Catani-Seymour, there's FKS, and so formally Catani-Seymour is worse because the scaling with the number of partons is slightly worse, but this is only relevant when you have like 10 partons and nobody ever has 10 partons. So whichever one you want to use is more or less a matter of taste. The real difference between them is that Catani and Seymour wrote an absolutely perfectly clear, understandable, lovely 100-page paper that you can sit down and read, and it'll take you about a week, and then you will understand everything there is about Catani-Seymour. And FKS wrote the most incomprehensible paper that you will never be able to understand in your life. To the extent that when I started working on this with Kirill Melnikov, I said, okay, I'll read the FKS paper, and he said, don't waste your time, you won't understand a word. And he's absolutely right, it is completely incomprehensible. From the title, you will not even, I mean, these are some of the best people doing QCD. I think they're absolutely amazing researchers. It's a wonderful method, but you looking at the paper, you will not even know what problem they're solving. I don't know how they manage to write, how such good researchers manage to write such a terrible paper. Oh, I forgot this is being recorded on YouTube.
I feel like Daniel, you seem to want to. Okay, last questions. If not,
yeah, so as I said, Andre, chatting with Andre yesterday, he asked me to say just a few words about my experience about, as I said, you know, I did my undergraduate here, did my honors and my master's thesis with Cesario, and I got my bachelor's in 2005, honors 2006, and master's 2008, and then I went to the UK for my PhD, and then as you heard, bounced around a bit, did postdocs in the States, then Germany, then CERN, and then now I've been faculty in Milan for the last 3 years or so. So let's say in general, when I moved from here to the UK, I would say that UCT compares very, very well. I was working with people who had done their undergraduates either at Oxford or Cambridge. I actually ended up working very closely with another PhD student who had got the top undergraduate mark at Oxford the year before. Very, very smart people. And I didn't feel particularly left behind. So I would say in terms of coursework, I was about 6 months behind, which was okay in the UK because nobody had really done quantum field theory at the time. So I was taught quantum field theory in an amazingly short amount of time as a PhD student. So the fact that I didn't have I mean, we had a relativistic quantum mechanics course, but it didn't have renormalization or things like that. So that I was taught as a PhD student. What we had at the time, and I don't know if it's still true, we had a very, very good computational physics course. Which I think a lot of other places lack, or at least lacked at the time, 15 or so years ago. So my colleagues at Oxford had never written computer code. And I'd already, I'd taken one semester of computer science, which I hated, but I'd done a lot of MATLAB programming with in my applied maths degree. I don't know, as I said, I don't know what it's like now. This is 20 years ago. I did the computational physics course, which at the time was taught by Roger Ferrick. I don't know if that's still going on. But I'd also done a lot of sort of little programming in the labs. So I knew my way around the computer program, whereas my colleagues, my fellow students at Oxford had never seen anything like that. So I was a little bit more prepared in that respect. And you should also remember that I say with 6 months, I was about 6 months behind, maybe one semester behind. But also remember that at least at the time, coming out of high school here, I was probably about a year behind where they were in the UK, because those students had all done A levels, which meant they'd all seen integration. Whereas I had seen integration at high school, but that wasn't the norm. So the assumption when I did Maths 1 was that you hadn't done integration, so they did integration from the beginning. Again, I have no idea if that's still true, but that means that essentially we had caught up about 6 months over the course of the degree. Chatting with Andre earlier, I would say that if I compare UCT to the University of Milan, it seems that where people are at the end of their bachelor's degree is roughly where our students are at the end of their 3-year undergraduate degree in terms of the courses taken. But school is 13 years in Italy rather than 12. So they probably, again, already start out a little bit ahead. And so that's just sort of maintained. But I would say that we do a 3-year undergraduate and then straight to the master's. I would say that the honors degree is basically at the end of so by the time you start your master's here or in Italy, you're basically at the same level. At least what you've been offered should be at the same level. We have the advantage that we have a taught master's program, so that gives us around about 3 semesters to give the students instruction in things like quantum field theory, fundamental interactions, which is basically standard model, QCD electroweak theory, etc. So that means that I would say that to the end of the master's, we are able to give more formal instruction than you are here. The flip side to that is that once you finish your master's here, you have 2 years of research experience. In Italy, by the end of the master's, you have 6 to 9 months at most. And I think this makes a huge difference in terms of a mindset. So when I started at Oxford, and they have almost no research experience before the PhD, I said I was working very closely with this guy, and he sort of, as I said, very smart guy, very well prepared for everything, knew a lot of things, but wasn't really aware of the sort of the time scale of a project, of a research project. So I was sort of used to from working with Cesario that the time scale for from the beginning of a project to publishing a paper would be somewhere between 6 months and a year, depending on how many problems you ran into at the beginning. And I think he was more sort of thinking, oh, it should be sort of a month to maybe 2 months. And so I was, I sort of, when I started, I was sort of in the mindset, okay, this is a long haul problem. And he was sort of thinking, okay, this is more of a sprint. So I think I had maybe some more patience or some more that sort of helped me. But as I said, and then again, if I compare with what I saw in Germany, I didn't do very much teaching in Germany, but again, I would say that the undergraduate course that I did will be very competitive with what was done in Karlsruhe. Again, probably there's some slightly, different, the emphasis might be slightly different. So for instance, I think one of the things that, because I did applied mathematics, I had a lot more instruction on partial differential equations, boundary value problems, etc., than students at either Karlsruhe or Milan get. But that's because of sort of the connection with the applied mathematics department. They might get, let's say, maybe more exposure to things like group theory or that's not really true. Functional analysis, maybe they do a little bit more. So, it's not that it's an entirely uniform thing, but it's a sort of, what we lose on the swings, we gain on the roundabouts thing. So, yeah, I don't know. So what I wanted to say is if you are thinking about going overseas for your master's or for PhD or postdoc, what you are studying now, the education you're getting in this building is absolutely competitive with anything you'll find around it. If you're interested in doing that and you want to chat to me, I'm very happy to talk about, what my experience was, how I should say also that the way I did it, the way I sort of approached trying to go overseas was entirely incorrect. It was it worked out in the end, but I was sort of fortunate. Because the way I was thinking about it is, I need to go somewhere. I don't have any money to do it, so I need to find a scholarship that will pay for me. And I think the way to do it is instead to find something you want to work on, find somebody who you can work with, and then typically, especially in Europe, they will, if they have a position open, PhD positions are treated more like jobs rather than being a student. So for instance, at my university, we have order 15 places for PhD students across the whole of physics every year, but each one of those comes with a stipend of a number, I don't know, maybe about a 1,500 euro per month, which is almost adequate. It's not at all adequate to live in Milan because Milan is expensive, but people, you will not sleep under a bridge. You will be able to afford a place to live and food to eat for the 3 years of your PhD. So and there's no question about getting a scholarship, this or that. Once you get the PhD position, it comes with a stipend, and this is typical of almost all places, I would say, within Europe, with the exception of the UK. The UK, you would have to pay the fees, and this means essentially getting some sort of a scholarship, or finding an advisor who has funding of their own, third-party funding that they can use to pay for your PhD. But my understanding is that is becoming more difficult. The US is a slightly different system. But again, if you get in, then there'll be funding. So at the same time that I was working with Cesario, we had another guy whose name was Bernard. He got into University of California, Los Angeles, and he was paid while he was there. He took an extra year or two to graduate because he had to do the qualifying exams, which are roughly speaking the second half of your honors. He was very clever about it because he had this opportunity of doing all these courses. So he did a lot of courses on statistics, which was important because he then went and worked in finance, and he's now working in New York in finance and making pretty good money, I would imagine. But he wanted to do that from the beginning, so he sort of that was sort of his path, and so he was able to exploit this opportunity very nicely. So, but I think there were 8, 9, or 10 of us as honors students. There were two German exchange students, but of the 6 or 7 South Africans, I know that there were PhDs, myself from Oxford, a good friend of mine from Cambridge, another guy from Zurich, another one from UCL, Bernard from UCLA, and if the other people are listening and I've forgotten them, then I'm sorry, I forgot you. I just, yeah.
I guess this depends a lot situations, but do you think doing your master's here is a bad idea and then going overseas, or going overseas in your master's year?
So the problem with doing a master's overseas is that is not. So with very, very few exceptions. So again, it depends. So this is within the UK and Europe. There are very few opportunities to get your master's funded. It essentially has to be a third party funding. Okay. Which is fine, but then third party funding typically is sort of for 3 or 4 years, and if you sort of use 2 of those for your master's, then you don't have enough for your PhD, or you go very fast PhD, which I don't recommend. So broadly speaking, I would say a master's here is a better idea. If you want to go to the US, it might be slightly different, and maybe Will probably has a much better idea, because my experience in the US was at Fermilab, so it was a national lab. We didn't have many graduate students. I know people who did their PhDs in the US, but I don't know the system very well. But I would say that in that case, it might be a better idea to go after the bachelor's, because then you do the coursework. I mean, master's is basically like in the US, a master's is the first half or first fraction of a PhD, right?
It sort of depends. So you're right about the structure in the US. So you do 4 years of undergrad, and then you go to postgrad, what we call postgrad here. And postgrad is the master's and the PhD in one lump. And the first 1.5 to 2 years is coursework, and then you do the PhD. That said, if you want to get into the very best US grad schools, you generally need to have a publication to your name. And it's exceptionally rare for somebody from UCP to have a publication before having a master's. It's very common in the US for foreign students to have a master's already and then come in to the PhD program in the US.
Which is exactly what Bernard did. So he had the master's from Cesario. He then went to LA, but then he did the qualifying exam. So I think he repeated a lot of the courses that he would have seen at the honors level, which again is fine because you are being paid while you do it. So it's not.
Well, also the expectation if you're at the really exceptional places in the US. I don't remember who told me the story, but it came, and maybe it was even to me. I don't exactly remember, but so it came in like going to do graduate quantum mechanics in the US. And he said, "Well, I've done graduate quantum mechanics already as an undergrad." And they said, "Of course you did."
Right. Yeah.
So the expectation is you've already had very advanced coursework, and they're going to build on that.
So I mean, what you say is exactly correct about the very best places, but I think, okay, my opinion, it's not necessary to go for the very best places in the US. They are. I would much rather. I think maybe you disagree with me, Will, but it's perhaps better to say I want to work on the following topic, and to go for a good person working on that topic, even if it's at a university that isn't your Harvard, your Stanford, your Princeton, etc. So for instance, so there's a fairly small perturbative QCD community in the US, but for instance, there are very good people at places like SUNY Buffalo or University of Florida, Tallahassee, Florida State. So if somebody said to me, look, I want to work on perturbative QCD, I would say, don't forget about Harvard, forget about Princeton. They're not going to do perturbative QCD. You should rather go to one of these other places. And I can, again, I'm talking about my field because it's the one that I know the best. But for instance, I have colleagues who have good permanent positions at some very good university who got PhDs from state schools. The way it works in the US, you have your very top elite Harvard, Stanford, etc., and then you have the state universities sort of a level below, well, multiple levels below. And then if you sort of have something like Michigan, Wisconsin, Virginia, all the California schools, Illinois, they are, let's say, a level below the top schools. I don't know, Will, if you would agree with this.
It's all over the show. Berkeley's a public school. And
Exactly. So I would say, again, if somebody said to me, look, I have an opportunity to get into Harvard, working on something that I don't know what I'll be working on, and it might be, the other problem is once you get into those places, everybody wants to work with these geniuses. And so it's very difficult to attract their attention. And so it's a sort of the question, would you rather work, with one of the best people in the world and you get, maybe 10 minutes a month with them? Or would you rather work with somebody who is not, at that genius level, but is, still doing good scientific work, and will be able to give you, an hour a day? Okay. And to me, I would rather take the latter option. And it's partly because I'm not a genius. Okay. So I don't want, and most people who are working in physics are not geniuses. There are geniuses in our field, but that's not the majority of people. Majority of people who have faculty positions are, I don't know, smart, but certainly not geniuses. And so it's almost a sort of yeah.
So when did you know you wanted to do for high precision particle physics?
So I actually didn't want to do it when I started my PhD. I started off wanting to work on astroparticle physics, looking at dark matter. And the person at Oxford who did that wasn't taking students that year because he had, I don't know, 2 or 3, however many, already. So he was feeling a bit, overburdened. And so that idea sort of disappeared in the first day or 2 that I was there. And then I spoke to some of the other faculty, and there were some other interesting options. There was a very strong string theory group, and they were taking people, and I sort of said, I don't want to do that because I thought I could probably handle the maths, but I wanted something where I had some connection with experiment. I didn't want something. If there's string theorists in the audience, I don't want to knock you, but it's sort of, I just realized it wasn't for me. I wanted something where I could, do something like this. And then I started working with Julia Zanarigi, and I kind of quickly realized this is actually something I like doing because, I think let's say broadly speaking, there are 2 types of physicists that can, 2 types of physics. There's one where you sort of, it's all about the idea, right? And this is a lot of the sort of the coming up with new theories. You sort of wake up in the morning and over coffee, you have a good idea. You do an order of magnitude estimate before lunch, write the paper after lunch, and that's it. But it's all about I'm being facetious, but it's all about the idea, right? It's all about getting that first idea. And then there's a sort of the stuff that I do where the idea, okay, there's still some ideas that you need to have, but it's much more about the actual calculation. If we had come along and said, oh, maybe you can use color coherence to write down a subtraction method at n and alone, okay, what a lovely idea. Nobody would have taken it seriously. Instead, we had to spend 12 months doing the calculation to show that you actually could. And then another 8 or 9 years afterwards trying to generalize it. And that I realized that was more the sort of stuff that I like to do. I like to sit down and just, kind of bash away at a problem until it gives in or I collapse. So it's sort of but again, what I want to say is that this is a personal thing, right? There's no right or wrong in it. It's what you like to do. And so I think I probably realized within about 6 months of actually working with Julia that, hey, this stuff is fun. I like, I'm enjoying this, even though it's frustrating, it's still a lot of fun. But yeah, but as I said, this I think a lot of the important thing about doing the master's degree here is figuring out what type of physics you want to do. Because what speaks to you, because a PhD is 3 or 4 years of incredibly difficult work where you basically just get knocked every single day, it just it's a constant attack on your ego. And if it's not fun, then you're not going to make it. It's just miserable. It has to be fun and work.
So should you gear your master's towards what you want to do?
I don't think so. Okay. I think, not that you should do something completely different. I think you should okay, so the first thing is that you of course what you want to do your master's in, if you do it here, is in some sense limited by the people that are available. So I'll give you an example. 2 years ago, I had a master's student come to me and said, I want to do my master's with you. fantastic, I'm very happy to have new master's students. He said, well, I know you did the mixed QC electroweak corrections to neutral current gradient. I want to do the two corrections to charge current gradient. And I said, that's a fantastic idea, but not with me, because I have no interest in doing this. I don't know how to do it. I literally don't know how to do it. So I said, not only am I not interested in doing it, I don't know how to do it. So you want to do it? You know, there's Alessandro, whose office is 3 doors down, go and knock on his. And so this is what I mean. You are limited in what you do. And I know, again, this is not UCT, this is everywhere, because you know every university has a finite number of professors who have a finite number of time. So, but what I think you should do is, well, try and let's say within your master's project, try and identify what about it is fun for you, right? Do you know what about it is interesting? The other thing that you should do is try and find out as much as you can about the field as a whole. Right, so you should be checking the archive, trying to understand it. One of the things that I was sort of, when I did my master's here, I was thinking, okay, I thought about doing my PhD overseas, but you know, I'm a local Cape Townian. I thought, you know, I can stay here. All my friends are here. My family is here. Do I really want to move halfway across the world? And then what really convinced me is that I was fortunate enough that Cesario sent myself and 2 other students to a school at the ICTP in Trieste. And when I was there were fantastic lectures by Michael Peskin and all these people. And I just heard about all the stuff that I hadn't really heard about before. And I thought, oh my God, this is all so interesting. And you know, there's a much bigger research world out here. I really want to go and do it. So I think having your finger on that pulse is very important. Also, it will help you to realize what you are interested in. Because if you see, so I was part of the PhD selection committee last year in Milan. I got about 200 applicants for order 20 positions. So that's typical. Now, if somebody, you see, but they're all, and this is I would say very typical of most places. But if somebody emails me beforehand and says, look, I've been working on this and this and this, you know, it's kind of connected. I know some of the stuff that you're doing. It looks interesting. Then, okay. At our university, there's really nothing we can do about it, but other places have a lot more flexibility. So for instance, somewhere like Germany, the ability of faculty to hire PhD students is much larger, in particular, or Switzerland, in particular if they have their own research program. So something like that, even if you see, also if somebody just has an idea of the kind of stuff they want to work on. So if I can come back to this to the student, when he told me he wanted to do that, I said, okay, look, I don't want to do that. So you know, if you want to do it, you don't do it with me. But you want to do this kind of calculation. Okay, this is a long, intense, difficult calculation. Fine. That's what you want to do. I have a different, long, intense, difficult calculation for you to do, where you will learn. And then, and he eventually did his master's. Because it wasn't, because I said, okay, you know, what is the essence of what you want to do? You're one of these lunatics who likes to sit down and do integrals all day long? Fantastic. I got a project where I need somebody to do integrals all day long.
So I guess then what I'm getting at is it's not really worth moving to a new university for masters if they are focusing on what you would possibly do in a PhD. That you.
No, I wouldn't say that. I wouldn't say I don't think there's a general answer to that question. Because if you're talking about a new university within South Africa, yeah, this is so in all these questions are very general, and there's always a non-scientific component to it, right? So you know, if you're talking about a university where you know you feel completely, you know, some people are very happy to get out of Cape Town. As I said, I grew up here. I can walk from here, where I did my entire undergraduate and master's, to my high school, to my elementary school in about 30 minutes, maybe 45. I was, so in that sense, I knew Cape Town, I'd experienced Cape Town. I was very happy to. That might be different for you. It might be the same, it might be the opposite, right? That's an entirely, you know, physics independent thing. If you've already said, okay, I wanted this area of physics looks cool, right? so I have an opportunity of doing something, this area of physics with, with a collaborator, in adverts. I'm saying bits because I was there at the beginning of the week, so I'm going to pick up that, right? So I have an opportunity to go to bits and do a master's. That that there's somebody there's nobody who's working on it here in Cape Town. I have an opportunity, or whatever. I have an opportunity to do it over there. Then, yeah, do it. Because in the worst case scenario, you will say, okay, that's not interesting, and then you'll be exactly where you were. In the best case scenario, you say, oh no, this is really interesting. I want to do my PhD on it. And then you'll have some, and then you'll say, okay, now I know even more about it. I know who the important people are, and I can start trying to figure out how I can go and work with them. So, as I said, this is what I meant when I said I think I did it the wrong way around. I found my advisor after I went to, and my field after I went for the PhD, and that was sort of kind of inevitable given the way the UK system works. But I think that perhaps a much more successful, as I said, I was very, extremely lucky. I think that a much more successful thing would be to say, okay, I'm interested in this type of physics, this subfield of physics. I want to continue with it. Who are the best people doing it? And how can I get to work with them? And typically, if you can answer those questions, well, frequently they will have money. If they don't have money for you, then you wouldn't work with them in any case. If they do have money, then you know. What I would advise.
Thank you.
But also, I mean, talk to the people here. Talk to Andre. They're the ones who know, and especially, usually we have some idea of the communities, right? So, I don't know, people who are working on corpuscle plasma and ion physics. But if a student of mine comes to me and says, look, I would like to do something like that, I would say, okay, I don't know these people, but I know people who know them. And so I then email people and say, okay, look, I have a student who's interested in working on this aspect. Is this an interesting problem? Who should they be working with? Who should they be writing to? Who has positions open? Who has a big grant that they're looking to hire a big team? That sort of thing. So this is, and again, you like everything else, it's a lot about the connection. So there are people here who have multiple decades of experience. I hope I'm okay advertising you guys, but I would say it's a good idea to talk to the faculty. I hope it's okay with me to say this, if you're not.
Send me an email anytime.
And likewise, if you think that what I've told you, or you think, oh, this looks cool, I would like to spend years of my life doing integrals and smashing my head against the wall. That sounds like fun. Then by all means send me an email. I'm very happy to chat about it. I'm happy to tell you more about it. You can talk now for another hour or so, hour and a half, if you want to know more. I'm very happy.
I think we need to bring things to a conclusion.
Yeah, because it's now been 2 hours, and as I said, I know that everybody just wants to go away for the moment.
Yeah. So let's thank the speaker one more time. Thank you for taking the time with us. Super.
No, I'm gonna actually go